Hello everyone, I am Sai from Team Mercedes. Today our team is going to present about global and local interpolation. So what is interpolation? Interpolation is a sort of estimation in the mathematical field of numerical analysis. It is a way of creating current data points based on the range of something like a discrete or set of known data points. Basically, interpolation are quality measures of the data. If data points are highly accurate, then we use interpolation. Whereas approximation means it is a value or quantity which is not exactly correct. If those data points are inaccurate, then we need to smoothen them out. So to smoothen the data, we use approximation. Approximation usually occurs when an exact form of or exact numerical number is or difficult to obtain. However, some known form may exist and may not be able to represent the real form, so that no significant deviation can be found in this approximation technique. So now moving on, what is the comparison of the both of these techniques, interpolation versus approximation? So in interpolation, there is no clear cut or right answer for these problems. Basically, there is no clear cut or right answer for any of the problems of interpolation and approximation. So it is the quality of your data. If your data points are highly accurate, then it makes sense to respect them as much as possible, and some form of interpolation would be appropriate. On the other hand, if you expect some uniform random noise to be associated with the data, then it makes sense to pay more attention to local averages to smoothen them out. In this case, an approximation scheme is more appropriate. So the given data never specifies a unique solution. There can be many nerves curves for a given set of data. So from given points in interpolation and approximation, we can draw many nerves curves, but each of them is right. We don't know which of them is wrong because every one of them is right. So there can be many mathematically correct curves for given data. So if continuity is wanted for a curve, then it must satisfy condition p is greater than or equal to r plus 1. Here p is called the degree of the interpolation. So if p is equal to r plus 1, then it is a condition for interpolation. If p is greater than r plus 1, it is a condition for approximation. So appropriately the techniques are used. Moving on, smoothness data reduction. This is for the approximation technique. Data smoothing is done using an algorithm to remove noise from a dataset. So data smoothing can be used to predict trends. This allows important patterns to more clearly stand out. This can be equated to the technique where the business people estimate the future. So if some data points are missing in between, then it is predicted and the data is smoothened out. The main advantage of the smoothness data reduction is it helps to identify real trends by eliminating noise from the data, and also it allows for seasonal adjustments of economic data. But disadvantages are removing data always comes with less information to analyze, which increases the risk of errors in analysis. Also, smoothing may emphasize analyst biases and ignore outliners that may be meaningful. So the data is lost while smoothing out some data. So this lost data may contain some critical information. So it is not always feasible to smoothen out the data, but overall it is a good technique to obtain perfection in the data. So the idea behind this is it can identify simplified changes. Also, it would make curves smoother. So, thus, as I said earlier, an investor can make predictions about how the stock may perform in the future. Moving on, application domains. So, where this interpolation and approximation are used. So, it is used to simplify complex functions by sampling data points and interpolating them using simpler functions. So polynomials are basically used to indicate interpolation and approximation techniques because they are easier to evaluate, differentiate, and integrate. So this is known as polynomial interpolation. And sometimes even splines can be used in place of polynomials, which are called piecewise polynomials, meaning they can change at different points. Global versus local interpolation. So this is comparison between two interpolation techniques called global and local interpolation. So global interpolation method, it applies a single mathematical function to all observed data points, and it generally produces smooth surfaces. So a change in one input value affects the entire map. Global interpolation is used when there is a hypothesis about the form of surface. So if surface is entirely known, then this global interpolation can be used. Similarly, local methods, it applies for a single mathematical function which repeatedly has small subset of total surface area. So it just applies to a small amount of data in an entire surface. So we should link these subsets on the regional surface to create a composite surface which covers the whole study area. So an example is given in this picture. So this is the example of global interpolation. This is a local interpolation. So global interpolation is applied to whole set of data points or subsets on a surface, whereas local interpolation is applied to just small or just a few data points on a surface. So this is the surface and these are the subsets of the surface or data points. So moving on, global curve interpolation. So it is the simplest method of fitting a different set of points within a B-spline curve. So we just fit all these data points on a B-spline curve. This data points can be obtained by using this formula over here. This is the formula of global curve interpolation. And moving on, next slide is parameterization. The parameterization is a problem of choosing a parameter value and not vector, which affects the shape and size of parameterization. So we often want a smoother surface representation, and hence the need arises to fit a smooth parametric surface through the vertices of the mesh. This requires making a suitable parameterization. Parameterization are also used for texture mapping and other processes in computer graphics. So there are three kinds of parameterization techniques. So first one is uniform parameterization, second one is chordal parameterization, and third one is centripetal parameterization. So uniform parameterization are used when only so uniform curves are to be obtained. But this method is not recommended as it can produce erratic shapes when the data is unevenly spaced. So when the data is unevenly spaced, you can see the erroneous curve in this. So this is the original curve, but the bends and even this bend is portrayed as straight line over here. So this parameterization should be avoided. So the next one is the chordal parameterization. Chordal parameterization is the most widely used method, and it is generally adequate. It also gives a good parameterization to the curve, in the sense that it approximates and it gives uniform parameterization. So there is very less error in the data over here. Even the curve fits almost perfectly in this. The third one is centripetal parameterization. As you can see in the chordal, when there is an edge in the curve, it gives some error in the data. But this chordal parameterization does not give errors when there is edge. But when seen the overall diagram, then it has somewhat more error than the chordal. So people use chordal parameterization these days other than centripetal if the data has a smoother curves and no edges. If there is an edge present, then centripetal parameterization can be used in the place of chordal parameterization. So moving on, uniform knot and averaging knot. These are the knot types. So uniform knot can either be uniformly spaced or they can be determined using an averaging method. In case they are uniformly spaced, this is the formula to calculate the knot. So basically this method is not at all recommended as even the uniform knot because it gives erroneous data. So only averaging knot is used because the data is accurate when compared to uniform knot. So this is a formula to calculate the averaging knot. We use all these formulas to calculate the global interpolation of the curve. So this is the global curve interpolation algorithm. So this algorithm gives out the value of p, that is the set of points. So This is the global curve interpolation function, which has all these inputs and outputs like NQRP, MUP. Here NQRP are the inputs and MUP are the outputs. So what do you mean by this? N means the number of points, Q is a set of points, R is the number of coordinates, P is the degree of curve, M will calculate in the formula is equal to n plus p plus 1, U is a not vector, and P is the matrix output. So uh, when you enter into this function, we first calculate the value of M, which is given by n plus p plus 1, and then we compute the UK, and then we compute the not vector U, and we initialize an array A to 0. So after initializing the array, we will iterate through a for loop which sets up a matrix. So to get the ith row, we find span and basis function. After finding this span and basis function, we will get the ith row of matrix. So after that, we will find this LU decomposition using this function, which has three parameters a, n plus 1, and p minus 1. So even in that, we iterate through a for loop which gives the number of coordinates of the matrix. So for j is equal to 0, j is less than equal to n, j plus plus. Another for loop, we will iterate through it. We will get the RHS of j, which is height coordinate of qj. And even we will use this function called forward backward, which has these five parameters. So in after this function, we will again iterate through a for loop which gives ith coordinate of pj, and we will get the solution from this. So this is the global curve interpolation algorithm, and this is an example of global curve interpolation in the NERV textbook. So we will be given a set of points. Qk is equal to these set of points. Initially, we will find the distance between them, that is qi to q0, q2 to q1, q3 to q2, q4 to q3, and we will add everything to get the value of d. So we will find its not vectors over here. This not vectors is calculated by this distance divided by total distance. So these are the average distances, that is averaging not vector is calculated over here. So by using these formulas, that is u naught is equal to 0 and uk is equal to k by n, we calculate the averaging knot over here, the total averaging knot. So here in this particular case, we get the value of j plus p as 4 is equal to p, the p value is 3, 1 by 3 into, we will add all these things over here, that is 5 by 17 plus 9 by 17 plus 14 by 17, as we get only up to 0 to 4. So the average is 28 by 51. This is, as this is the average value, uh, we place it in the not vector matrix, like in the between, and the values before this becomes 0 and after this becomes 1. So this is the not vector, and after obtaining not vector, we place them into the matrix, and this is how we will get the coordinates of global curve interpolation. Moving on, this particular curve shows interpolation of general data set with 2 and 3 and 4 degrees. That is, this is 2, this is 3, this is 4, and also it has this solid dashed and dotted curves respectively. And this figure depicts how global interpolation, it cannot handle collinear data points, that is the dashed line. So as you can see, if there is a dashed line, then there must be some curve, because the global interpolation works like that. So global curve interpolation with n derivatives. So global curve interpolation with n derivatives is similar to the global curve interpolation without n derivatives. So it is not uncommon for derivative vectors to be specified as input data. We use the same solution as specified to global curve interpolation. So we first compute parameters uk corresponding to the points qk. We then compute a not vector u. We evaluate the basis functions to set up a system of linear equations, the control points as unknowns, and then we solve the systems. So only two steps are slightly different from the previous case. Each derivative gives rise to one additional knot and control point, and hence one additional linear equation. And again, let qk, that is k is equal to 0 so on up to n, be points, and assume d naught and dn are the first and last derivatives, and we want to interpolate this data with peak degree curve, that is cu is equal to I is equal to 0 to n plus 2 nip u of pi, and then we compute the uk, k being 0 up to n. We compute this using the knot vector and the approximation equations, the parameterization equations, and then we set m is equal to n plus p plus 3, and then we obtain m plus 1 knots by using this formula. And we can see this formula is similar to the knot vector formula, and we pick two additional knot equations, that is minus p naught plus p1 is equal to upi up up plus 1 by p into d naught, and minus p n plus 1 plus p n plus 2 is equal to 1 minus um minus p minus 1 by p into dn. So these are the two additional equations that we obtain here and compared to global curve interpolation. So thank you, and Rupesh will continue with his presentation now.
Hi all, this is Rupesh. I will continue from here. I will start with this cubic spline curve interpolation. The previous methods are valid for any degree of p greater than 1. If p is equals to 3, there is an algorithm which is more effective and yields a better traditional cubic spline. The UK are computed as previous. The knots are mentioned here. In other words, the interpolation occurs at the knots. The first two and last two equations are respectively mentioned here for the knots. This figure shows cubic spline interpolant compared to regular cubic interpolant obtained by using knot length parameterization and knots computed by averaging. A global cubic curve interpolant with different kinds of derivation directives are mentioned here with n is equals to n plus 1 and n plus 2, which gives q of n. These can be solved differently and it can be solved directly, recalling that there are only three non-zero cubic basic functions at the interior knot, and remaining n minus 1 equations have the form of uh, basic equations have this form. Uh, here we have this equation for qk with all the values. Here the k value is from 0 to n minus 1. Uh, by setting those, we will get these ak, bk, and ck values, which yields the tridiagonal system. Here we will see how the first derivatives happen and what is the algorithm included in this tridiagonal system. Here this is just a function. We want to solve the tridiagonal system from cubic splines. All the inputs that are mentioned here are n, q, u, and p, and we want to get a final output from for p here. We'll use something called basic functions that will take the input as u and abc, and yeah, this is all what happens. We will use some basic functions for different types of iterations, and the basic output that we get is p. Yeah, the parameters here mentioned, the parameters uk are computed using these below equations with the number of knots, like two types of n plus 1 plus p plus 1, and they should be chosen to reflect the directions of uk. For p is equals to 2 and p is equals to 3, the satisfactory choices are as below, and these equations are respectively merged in alternating fraction to yield these linear system equations. For example, if p is equals to 3, These denote how the UK and these values differ with it. These are a system of equations that we get for different values of k from p is equals to 0 to p4 that is mentioned here, and as it is follows with n here. This figure shows the cubic or interpolant for with varying tangent derivatives at each point, and this figure shows the control points for quadratic Bleach-Span curve interpolant to data with specific derivatives. We now turn to global interpolation of surfaces. We are given a set of n plus 1 to data points, and which has a qkt as the derivative, and we want to construct a non-rational p comma qth degree b-spline surface interpolating these points that gives the summation. This qkt is formed by using a function is suk and vt, and this is summation of the all the inputs given here. Again, the first order of business is to compute reasonable values for uk and vt, and the not vectors u and v. We show how to compute uk comma vk or analogous, and a common method is to use these above equations to compute parameters from u0 to un, and for each l, and then we obtain each uk by averaging across all UKs from L is equals to 0 to M, uh, where for each fixed L, UK and K is equals 0 to N are computed. An efficient algorithm will follow here, and it computes both UK and VK. It requires any local arrays from length n plus 1 to m plus 1. The distances q of k comma l comma q of k minus 1 from k is equals to 1 to n are similar to the v direction. The function distances distance 3D computes the distance between two three-dimensional points. This algorithm handles the case where the total chord length of a row is equals to 0 and necessary condition is three-sided surface is being constructed. Now for the computation of the control points, it clearly represent that n plus 1 into n minus 1 linear equations is unknown. However, since S of u comma v is a tensor product surface, the p I comma j can be obtained more simply and efficiently as a sequence of curve interpolations. For fixed L, we write the equations as here. Notice that in this above equation is just a curve interpolation through the points q, k comma t, where k is equals to 0 to n. The r, I comma t are the control points of the isoparametrical curve on s, u comma v are fixed at v is equals to vl. Now fixing I and letting L vary, equation 9.27 is curve fitting through the points r I comma 0 to r I comma m, with p I comma 0 to p I comma m are computed using the control points. Thus the algorithm is obtained as p I comma j. Using u and uk, do m plus 1 curve interpolations through q0 comma l comma qn comma l. This yields r I comma t. Using v and vl, do n plus 1 curve interpolations through r I comma 0 to r I comma m. This yields p I comma j. Clearly, this algorithm is symmetric as the same surface obtained by doing n plus 1 curve interpolations through q k of 0 to k of m to obtain the r kj. This is control points of parametrical curve is u of k comma v. Uh, then doing m plus 1 curve interpolations through the r0 comma j to rm comma j to obtain pi comma j. The curve for this equations is here. Yeah, this figure shows interpolating in v direction through control points of uh, u directional interpolants, and this figure shows the surface interpolant showing control points. This figure shows the data points of test surface interpolation, and this figure shows the degree of parameterization in the knot. And the derivative constraints can also be incorporated in global surface interpolation. Conceptually, the derivative formula of can be used to define an additional linear equation for each derivative constraint specified. Unfortunately, if the number of data constraints is not the same in every row or column, it becomes more difficult to solve for unknown surface control points using a curve interpolation in two directions. I described previously, we however with a clever use of curve knot intersection and surface knot removal, one can adopt algorithms to handle partial derivative constraints at individual data points. Finally, the local surface interpolation methods are well suited to handling derivative constraints as they require derivatives at each point anyways. This figure shows how the data containing coplanar points, and this figure shows how the interpolating um how the interpolate how the interpolating surface will occur. And from the next slides, Andrew will continue with the presentation.
Local parabolic curve fitting. So, for local parabolic curve fitting, first we start with a simple two-dimensional non-rational quadratic scheme. Let the set qk be points in xy plane. The tangent estimation scheme to compute the corresponding set tk, and lk denotes the director line defined by the point qk tk, and rk is the intersection point of lk minus 1 and lk. Assuming that the intersection exists and that gamma of k minus 1 is greater than 0, where rk equal to qk minus 1 plus gamma of k minus 1 tk k minus 1, and when gamma of k is less than 0, rk equal to qk plus gamma of k tk. Then we choose our control points q0, r1 to rn qn. Let u of 0 equal to 0 and u of n equal to 1. If the set u of I is any sequence of numbers satisfying u of I minus 1 less than u of I less than u of I plus 1, then the control points together with the knot vector are as shown here, which is the set U, and they define a non-rational G1 continuous quadratic B-spline curve interpolating the set QK. The choice of internal knots does not affect the shape of the curve. They affect only the parameterization. It is possible to choose the knots so that the resulting curve C1 continuous. In doing so, we can remove the control points q1 to qn minus 1 and one occurrence of each of the interior nodes. We simply equate and start and end derivatives at qk minus 1 and obtain the following formula, which is uk equal to uk minus 1 plus uk minus 1 minus uk minus 2 mod of rk minus qk minus 1 divided by mod of qk minus 1 minus rk minus 1, where k is from 2 to n. C1 continuous curve interpolating the set Qk is then defined by control points Q is 0, R1, so on till Rn, Qn, and the knots in the set U as shown in here. One must pay a price for the C1 continuity and the reduction in the number of control points, namely in the parameterization. Both figures show this. The curve in these figures is marked at equally spaced parameter values. In the first figure, the knots were computed using the equation uk equal to uk minus 1 plus uk minus 1 minus uk minus 2 mod of rk minus qk minus 1 divided by mod of qk minus 1 minus rk minus 1, where k is from 2 to n, and in the second figure we do it using the chord length parameterization. Now we detail the two special cases which arise when computing the RK. Case A, Tk minus 1 and Tk are parallel, hence Rk cannot be computed by intersection. Case B, Rk can be computed but gamma of k minus 1 and gamma of k do not satisfy the equation Rk equal to qk minus 1 plus gamma of k minus 1 tk minus 1 when gamma of k minus 1 is greater than 0, or Rk equal to qk plus gamma of k tk when gamma of k is less than 0. The collinear segments case applies if tk minus 1 and tk are both parallel to the chord qk minus 1 and qk. We handle this equation simply by setting Rk to half of Qk minus 1 plus Qk. All the special cases are handled by creating two parabolic segments between Qk minus 1 and Qk instead of 1. Thus, we must compute three additional points Rk dash, Qk dash and Rk plus 1 dash. Setting Rk dash to Qk minus 1 plus gamma of k Tk minus 1 and Rk plus 1 dash to Qk plus gamma of k plus 1 Tk and Qk dash to gamma of k Rk plus 1 dash plus gamma of k plus 1 Rk dash whole divided by gamma of k plus gamma of k plus 1. It remains to determine reasonable choices for gamma of k and gamma of k plus 1. If tk minus 1 and tk are parallel but not the chords qk minus 1 and qk, then we set gamma of k, which is also equal to gamma of k plus 1, to half of gamma of k minus 1 qk. This is illustrated in the first figure where tk minus 1 and tk can be seen parallel to each other. In the first figure, it is the case for 180 degrees turn. Now consider the case when tk minus 1 and tk are not parallel, which we can see in the second figure where they both are not parallel to each other. So here gamma of k and gamma of k plus 1 should depend on the angles theta of k minus 1 and theta of k subtended by the chord qk minus 1 qk and the tangents qk minus 1 and tk respectively. Both of the figures shown in the slide are samples of parabolic curve fitting, but using different methods. In the first figure, the tangents are computed by Bessel's method, and in the second figure, the tangents are computed by Akima's method. We can see in the second figure how collinear it is and how collinearity is maintained in the figure with those curves and everything compared to the first figure. So these are some sample figures of local parabolic curve fitting. In the first figure, the no corner option is selected, resulting in perhaps unwanted smooth connection of each segment. But in the second figure, corner preserving case is selected by using the same algorithm, but the flag setting is different. So we can see the difference in corners in first figure and second figure. The corners in the second figure seem to be more sharp compared to the first figure, and the third figure shows the profile of a shoe sole obtained using this interpolation method only. Rational quadratic curve fitting. The previous method can be modified to produce rational quadratic curves also. All the weights at qk are set to 1 and weights at rk can be freely chosen. For example, some applications may desire the segments to be more circular rather than parabolic. More specifically, for k equal to 1 to n, a iconic arc is defined by qk minus 1, rk, and qk, and the weight wk at rk. The wk can be set as follows depending on conditions. If qk minus 1, rk, and qk are collinear, then set wk equal to 1. If the triangle is isosceles, that is qk minus 1 and rk mod equal to mod of qk-rk, then set wk according to the precise circular arc. If the triangle is not isosceles, then set wk in the following procedure. The procedure can be followed step by seeing the figure over there. Let m equal to half of qk minus 1 plus qk. Set S1 to be the intersection of MRK with the bisector of the angle RK QK minus 1 QK, and set S2 to be the intersection of MRK with the bisector of the angle QK minus 1 QK and RK. Then set S equal to half of sum of S1 and S2 with S as the shoulder point by using the below equations, which are S equal to 1 minus S into M plus SP1 and S equal to W1 by 1 plus W1 and W1 equal to S by 1 minus S to compute the weight Wk. Here we can see an example of rational quadratic curve fitting, and we can see that the circles are precisely reproduced from the 4 points and the 2 corners are preserved by setting the corner flags. Local cubic curve fitting. Cubics easily handle three-dimensional data and inflection points without any special treatment. Here, we derive a general fact about cubic Bezier curves, which is of interest in its own way. Let P0 and P3 be two endpoints and T0, T3 be the corresponding tangent directions with unit length. It is possible to construct a cubic Bezier curve C of u where u can be either 0 or 1 with these endpoints and tangent directions and satisfying alpha equal to mod of c dash of 0 or mod of c dash of half, or which is also equal to mod of c dash of 1. By seeing the figure, we can say that the speed is equal at start point, midpoint, and at end point of the curve also. The above equations which are shown here, like c dash of 0, c double dash of 0, c double dash of 1, dash of 1, imply that p1 equal to p of 0 plus 1/3 of alpha t0 and p2 equal to p3 minus 1/3 of alpha t3. This algorithm yields n Bezier segments, each having speed equal to 1 at their end and midpoints with respect to their parameter ranges from UK to UK plus 1. Thus, a C1 continuous cubic B-spline curve interpolating the UK is defined by the control points Q0, P01, P02, so on till Pn-1 to Qn, and the knots are shown in the set U. We can see all of this and understand it by looking at the figure shown in the slide. These are some examples of local cubic curve fitting. The first figure is designed using the previously described method, and the curve is marked at points corresponding to equally speed parameter values. The second figure is another example of this interpolation, and we can notice how the collinear points are fitted by straight cubic segments.
Hi, this is Pooja. So now my topic is regarding bicubic interpolation. So when it comes to interpolation, basically the general meaning of interpolation is that inserting one thing into some other thing where its nature, the original nature of the object or a material is going to completely change is known as interpolation. So when it comes to bicubic interpolation, bicubic surfaces are nothing but the extension of cubic interpolations where only the dimensions of the general grid and the points change. So when it comes to interpolation, what does that actually means? It's something in detail curving or smoothing a object or a surface to its nearest neighbor, interpolating something like smoothing an object. Suppose if we take a square, how to transform a square into a circle. It's something in that way where you smoothen its edge curves, and then make it more detailed and finer in details. So when it comes in that way, it's sort of that. So in the first case, this is the case one and this is case two. So in the first case, symmetric body here, you can see the deformed curve, this orange line over here. So by changing even one grid or one dimensional values like plots on a graph sort of. So if you modify just one, the other is gonna be like curve. So in this image, if you see the blue color surface over here, it's something the original surface, and the red surface beneath the blue is something which is a modified surface by changing this orange line from this among these gray lines. So this orange line is something a new position where we insert, so it adds more details in it. This is another example of bicubic interpolation. Here we can see everything are in form of squares and rectangles, which are of a sharp kind of edges over here. So that's the detail I'm talking about. So yeah, not values. When we wanna talk about the not values, alternate not values are represented with these mathematical representations and by B-spline curves, which is represented as A of U. So here we can see the mathematical representation and the degrees and the dimensions over here. So these are the mathematical representation. So based on these equations and all, we can, you know, change from uh, a little detail, I mean, version of this to a more detailed version of here. Something, yeah, when coming to comparison, so the definition of Bezier curve and the B-spline curve is something like n degree of the polynomial with n plus 1, which is only n plus 1, which only sees the alternative data point, something like a graph. But when we see B-spline curve, it's something in more detailed and a bit of extension of the Bezier curve. So here it's something we only change the degree. So when we look into the mathematical formula of this Bezier and the B-spline curve, here we can see the limits are like from 0 to 1, where only when the limits are minimum, you can't expect more details in the figures, but rather than the when the limits are like max, so you can expect more details, curving, and detailing, smoothing and curving, and more graphical and animated representation rather than the limits which are just like the side and something. So when we talk about the advantages and disadvantages of these curves, so Bezier curves can pass smoothly through number of data points. So here, if you want to see this curve representation over here, the same curve is represented over here, but with a more curvy nature. So this is something you can get a blueprint basically, but this is a building sort of thing. So for before a building, you would like to have a blueprint, something like a rough representation, but this is good for representing what are we expecting. But this is something an original plot, so that you can add more details over here. Uh, the same thing with the disadvantage, which is like we can't go to like highest degree and all because there is a limit of this thing 0 to 1, where the n value is in, I mean, we have a I value of n something, we represent this nth value, but the u value is something like very restricted, so we can have only the basic blueprint. Here when it comes to advantages and disadvantages, this is a local central over the curve, so this is something which is independent of the data point, something like you can't expect a curve having an other curve within the curve, something like this. So this is a curve, we can have a look, and then this do have an angle which is changed from the initial one. This is something like a straight line and a little curve, but this goes in detail form of curvation. So that thing is over here. So bicubic interpolation. So these are the mathematical representation of the things which I have spoke before. So each and every detail of the data points which we use over here or something that we derive from this, and then this is something a thing. So here you can see a blue color with a random figure, so which with the data points and then transforming with the mathematical representation, you can see a shape is going to form over here. And if you interpolate this more, you can get a shapes like triangles, circles. I mean, here there are triangles and squares though, but you know, from this rhombus kind of thing you can get a circle, and from this weird shape of blue thing you can get a blue a rectangle, something like that. By using this mathematical representation, we can always do these kinds of transformation. So here are the good examples. If you want to see the smoothing of the surfaces, so these are something here, and then this is like something more smoothing surface. For getting a circular form of this representation, you should smoothen these all and get a nice detailing and all. And then here also same. So this rectangular, cubical and everything, these are like something we want to represent into more detailed in every function of these. So when it comes to adoption, so here there are two figures A and B. So when you want to comes to adoption, the MSC surfaces here, the first one is like only twice interpolated, where the second one is of like 4 times interpolated. So you can see the detailing of these things, where this is like a rough thing and here, but this is like more curvy in nature and more detailed in nature. So yeah, interpolation. So here as we spoke, this is a native interpolation where the detailing is like not that the structure of the image and the detailing isn't, you know, curving the colors and everything, but the detailing over here is like more precise rather than the native thing. By using the degree and the polynomial over here, each time you interpolate the original image to the last image, the detailing and the transformation of the colors and the shapes and the structures, everything happens over here. So this is another example. So here we can see a rectangle and square type of this original image is like changing into curving and detailing. You can also see this view, this is like a side view thing over here, where this is like just a line, but here you can see a detailing over here, and then a beneath of this you can even see the detailing. So this is something known as bicubic polynomial. So when it comes to design examples, as I already spoke about bicubic interpolation and interpolation things, the nearest value, this is a sort of graph which is like plotting digital line graphics, something like plotting of these graphs, hydrographic layers and something. We use all these kinds of graphs over here. So the red thing over here is something which is an irregular spaced spot which should be corrected. So the purple grid over here, which is like a correct version of this nearest red thing. So this kind of like something very minimal kind of difference. The maximum difference would be like 50. I would say approx. So all these could be like the representation over here too. So this is a mathematical representation where the nth value is being chosen by us based on the dimensions and the data points. The z value is something the irregular points. The red color is like a z value, and the d color is something which we want to form. So by calculating everything, suppose if we have taken this thing, the mathematical representation of the pth value to be determined, just like the way we should calculate this. So this is my presentation.
Hello everyone, Sai here. I'm going to discuss about this GM lab today. So this is a basic circle which I created in 2D animation of Blender. So when a circle is created, uh, I created a circle at the data point 0 and another circle at data point 20. So when applied the interpolation technique, this data point, so this figure at data point 0 and this figure at data point 20 need to be interpolated. Means if I go in between them and I click this interpolation button over here on Blender, the figure must appear in between, even if data points are not there in between. So when I clicked it, the output was like this. So as you can see, there is a circle created in between. I'm sorry. So that was the thing. Thank you.